So in this video, we'll be covering current and resistance and resistors in series and parallel circuits. So we know that a resistor basically limits the flow of charge in a circuit, and there's an off-mix device where we have the formula V equals IR. So whatever current that flows through this resistor, we can always find the resistance if we have voltage. So most circuits have more than one resistor, but if several resistors are connected together and connected to a battery, any battery, voltage, whatever, the current supplied by the battery depends on the equivalent resistance by the circuit. So if we have a basic circuit, we can basically make an equivalent circuit, which makes it more simpler to understand and more simpler to calculate. So here we have a series circuit, so it's just something really basic. So we have like 3 resistors, so R1, R2, R3. Now here we know that to find the total resistance, we just add them up. So it's nothing too complex, but sometimes, like, this is a series. Now if you want the parallel, then you can have something like this, something a bit more complicated, that just goes like that. So because there are 4 resistors in this circuit, we know that there's going to be different current stuff flowing through here, whereas here there was only one constant current that was being supplied throughout the entire circuit. Now we have 4 currents, and that's why we're going to have different voltages at these points, but this also depends on the resistance. So for instance, if we have two similar resistors, we're going to have the same voltage at this point, but the formula for this is going to be 1RT equals 1R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. Now whatever answer you get from here, you need to do 1 over answer in the calculator, and that'll give you your total resistance. That's why whatever answer you get here, RT, is 1 over RT. So always remember that you have to do 1 divided by your total resistance. So we can also add a bit of Kirchhoff's voltage laws in here. So for instance, we have a battery, so that's plus minus, that goes through resistors into ground, because it wouldn't work, and then R1, R2, R3, and that's just from point A to B. So it's just a standard variable V. We know that this is voltage 1, voltage 2, and voltage 3. So because these are in series, we can just add these resistors up. So the circuit would become something like this. This is basically the equivalent circuit. So it's just the same circuit, but because these are in series, it's been added up into one resistor, which will give us an equivalent circuit. Because we know in this circuit, for example, we know that there's only one constant current that's flowing throughout each resistor. Now because there's only one constant current flowing throughout each resistor, we can just add these up, and we can just simply make an equivalent circuit like this, with the battery being unchanged, of course. So we know that total current in the circuit depends on the voltages and the total resistances. So for each resistor, there's always a potential voltage drop that occurs that is equal to the loss of electric potential energy as current travels through the resistor or through the entire circuit. So according to Ohm's law here, we know that the potential voltage drop across a resistor when the current flows through is calculated through this equation. So we know that so when we're dealing with circuits like this and making them into an equivalent circuit, we also like to use Kirchhoff's voltage laws and Ohm's law to find what we're looking for. So we know that the total voltages, the voltage in a closed loop is equal to 0, and this is just Kirchhoff's voltage law. So if we're looking at this the circuit, for example, and why we get this formula, especially, we can make a simple equation. So here, because it goes from minus to positive, it will be positive, and because when the current flows through this point here, it's going to be positive, negative between each resistor. So that's why we get a voltage drop. We're limiting the voltage. So it will be minus V1 minus V2 minus V3, and that equals to 0. So now let's put all of them on the other side like this. And we know that the formula for voltage is IR1 plus IR2 plus IR3. We know that because the current is the same throughout the circuit, is going to be the same current, but the only thing that's changing is the resistances. So we can put the I outside the bracket like this, and if we want to find R, or current, we just simply write it like this. Something simple. So when we're at this point, because we know it's obviously a series circuit, we can just write it as this, or RT. It doesn't matter. So since the current through each component is the same, the equality can be simplified by, as we know, equivalent resistance, or RS. We can do that. So we know that resistors in any circuit can be very complicated, because there could be like 10 resistors and they can be connected by junctions, and it can just get confusing. But here I'll just show you the really basic circuits, but then it'll get more complicated. So here we have a basic circuit, R1, R2. We know that the total resistance for here would be R1 plus R2. So this is just really simple. We just add the resistors up. Here in this circuit, we got another voltage. This is R1, this is R2. RT is going to be 1 over R1 plus 1 over R2 minus 1. Now what that minus 1 means is that whenever you calculate this answer, you would need to do 1 over the answer. So for example, if R1 was 5 ohms and R2 was 6 ohms, we would do 1 over 5 plus 1 over 6, and then that would give us 1 over, or 11 over 30, and then we do 1 over 11 over 30, so 1 over the answer, so 1 divided by answer, and that would give us 30 over 11. So it's always going to be the inverse, because it's 1 and the answer is just 2.727 ohms. So that's just really basic. Now again, if this was in series, we'll just do 5 plus 6, which is 11. So one of the main reasons for this is just because the current. So the current here is, there's one current throughout the circuit. Here there's 2 currents, so the voltages are going to be different, of course, at each resistor if they're different. So let's say that we have let's say we have another circuit. So here we can have like 24 volts, for example, and here we have another resistor. Here we have a resistor like this, and here we have a resistor like this. Here it could be like 90 ohms, here it could be like 20 ohms, and here it can be like 110 ohms. So we have resistor 1, resistor 2, resistor 3, and we have a voltage, so that's positive and negative. So here, looking at the circuit, we know that we have 3 resistors, and we don't know if they're in series or parallel. So an easy way of knowing if they're in parallel or series is just by looking at this. So here we know that these resistors are in parallel, so we'll need to calculate them in parallel and add them with the series resistance. Now we can't add the R1 and R2 in series because there's a junction connecting this resistor right here. So what we need to do is calculate the total resistance of these resistors. So 1/20 plus 1/10, and that will be over -1. That will give us 1/20 plus 1/1. So that will give us, we can leave it as a fraction for now, so 220/13. So now we can rewrite the circuit. So everything's the same except for R2 and R3. So here the resistor stays the same, but now we added our new resistor, our resistance that we calculated to be 220/13. So this is R1, and here we can just say it's R2, it doesn't matter. We calculated this in parallel, so now we can add these up. We know that R1 is 90 ohms, and here, remember, because they're in series now, we can just add them up using this formula. So 90 plus 220/13, and that will give us 106.92 ohms. All of these resistors are in ohms, so the final answer will be in ohms. Now we can find the current now if we wanted to, flowing throughout the circuit. Because we added these in series, the circuit is now going to become something very easy to read. So that's 24, that remains unchanged, and this is just 106.90 ohms. This is the circuit that we made from just this. So as you can see, when we simplify like this, we can calculate it to be more simpler. So using Ohm's law, we can find the current. So I equals V over R. 24/106.92 gives us 0.22 amps. So this example is very simple. This is probably a very commonly used example, I'll be honest with you, but here is also quite easy to understand. So here we can see it's connected. So first we can see that 8 ohms and 7 ohms are the resistors with these values are connected in parallel. So we can just add them up, 1/7 plus 1/8. So that would give us, that'll give us 56/15. So rewriting the circuit, we know that we just calculated this resistor. So we calculated this resistor, so that can just be here. So 56/15. and then this will be 10, this will be 6, 5, 10, 20 volts. So now we can see that these are in series, so we can just add them up, and that will give us 206 over 15. So now we can get rid of this and add another, and we can just add it like this. And again, now we have another problem. We have these resistors in parallel, so now we have to add them up. So 206, 1 over 206 over 15 plus 1 over 6, keep that in a big bracket. And then when you're putting these values in the calculator, just always make sure you're writing it correctly, because you're adding fractions and then you're adding the brackets, it can get a bit confusing. So that would be 309 over 74. And now the circuit will look something more like this. So that would be 10, that will be 5, and that will be here. So 309 over 74. Now, because everything's in series and everything looks more nice, we can just add 10 plus the answer plus 5. And then our circuit will look something like this. So it'll be 19.75, and that'll be 25 plus negative. Now, as you can see, the circuit is obviously quite complicated, and we calculated the equivalent circuit to be something like this. Now, would you rather find the current throughout each circuit over here, or would you rather simplify everything and put it into this equivalent circuit? I think this is much more easier to do. Obviously, all we did here was we combined the resistors, we combined the total resistances to give us something like this, and here we can actually find the current, and you can basically say that this is Kirchhoff's equivalent circuit. You can convert it into a Norton's equivalent circuit, whatever, but here we can find current easily now.